All right, it's my pleasure to introduce Josh Ruderman. Don't really have to introduce him to most people here. You all probably know him, but just in case you don't. Josh got his undergraduate degree at Stanford, then went to Princeton, where he got his PhD in 2011. He was a Miller Fellow at Berkeley after that, and then came here, joined the faculty in 2014. We've been quite fortunate to have him as a colleague. Especially, I've been very fortunate to have him as a colleague since he arrived. His work, of course, he's younger than me, so his time horizon is longer. So he's one of the experts, not only thinking about the possibilities of colliders today, but of colliders tomorrow in the long term. He's also thought actively about new models of dark matter, going well outside of traditional models that people have considered previously. And along the way, he started thinking about all sorts of different novel astrophysical and otherwise means of looking for the hidden universe. So he's going to be telling us about some of these things today. As he alluded to in his abstract, this is inspired by techniques from the Department of Defense. So I assume everybody has their security clearance. If not, you should probably leave. Okay. All right, thanks. Go ahead.
Thanks, Neil. Thanks, everybody, for coming. So I'm going to tell you about things that we know and things that we don't know, and I'll jump right in. So in particle physics, the big game is still the Large Hadron Collider. This is this collider located outside of Geneva on the Swiss-French border in this 27-kilometer tunnel. This shows the location. I spent the spring semester of 2018 at CERN, so you can actually see in this picture my apartment, my former apartment. It's about over there, I guess. But anyway, in this tunnel, we accelerate protons to the highest energy that we've accelerated protons to. So each proton has energy 6,500 giga-electron volts. The mass of one of them is about 1 GeV, so the energy is much more than the mass, highly relativistic. These beams are brought to collide at special collision points located in large detectors that are like cameras. Atlas, our experimental group here at NYU participates in Atlas. Okay, so we collide these protons. The protons are destroyed in this collision. And we literally do alchemy in particle experiment because we create new things that were not there initially out of the energy of these collisions. And in this way we find out what exists and we find out the properties of what exists. And I'm going to give you a one-slide sort of executive summary of what the LHC has achieved so far. So famously, the LHC discovered the Higgs Boson. In fact, this is now old news, back in 2012. There's a Nobel Prize for the theorists after. We now precisely know its mass. So to precision better than 1%, this is a recent determination. So the Higgs is the first fundamental spin-zero particle. It's responsible for the masses of other particles, so it's very important. Okay, so that's number one, the Higgs was discovered. And number two, other new particles were not discovered. And many were looked for, so there were many opportunities to find new particles, and instead we have exclusions. So this is one randomly selected example from CMS, not chosen because they're looking for something I suggested. But I'm not going to explain the details, but I'll just say they're looking for a new colored particle called the gluino. And here the x-axis is the mass of the gluino, and they exclude it within the region bounded by these curves. And if you just look at the number, well, yeah, the y-axis is another massive particle it's decaying to. But if you just look at the numbers, you're going out to 1,600, 1,700 GeV. Before the LHC started, the mass of the gluino could have been just a couple hundred, say 200 GeV, 300. And there are other cases where the bounds go past 2,000. So anyway, it hasn't shown up. It could have, and there are very impressive constraints on its mass. And this is just one example of a diverse set of new particles that we're looking for that we haven't seen. So that's sort of the two bullet point summary. Higgs was discovered and not other new particles. Okay? And I want to just tell you where we are and where we're going. This plot shows the luminosity on the y-axis, which is the number of proton collisions, luminosity by year. So it started in 2010. We're here now in a shutdown, which is why it's flat, long shutdown 2. And now I'm going to show you where we're going. Okay, that's where we're going. The LHC is projected to run until about 2037 or 2038. And it's projected to collect about 20 times more proton collisions than we have so far. So we're only actually 5% of the way through this long-term program. And one kind of question I want to think about in this talk, I want to ask what can we learn with the remaining 95%, given the current status that I just summarized. Okay, so that's where we are and where we're going. And I want to emphasize there are still cases where we can discover new particles, even given the fact that we haven't seen them so far. So here I'm choosing one example. for the experts, this is we knows, but for everyone else, I'm not going to talk about this in careful detail, but I'll just say you're making two new electrically charged particles, and you can roughly think of them as heavy fermions. They're decaying to a lepton, a neutrino, and another heavy particle that you can roughly think of as a heavy neutrino. It could be the dark matter. Here the x-axis is the mass of this heavy particle you're making. The y-axis is the mass of this other heavy particle. The shaded area is the region that's currently excluded at the LHC at 2 sigma statistical significance. The blue dashed line bounds the region where you could still have a discovery with 5 sigma statistical significance using the remaining 95% of the data. And it's still a pretty big region in this example. So just to show you that there are cases where we could still have a discovery that would be super significant and Nobel Prize winning if it's in there. If it's out there, then not. This line is where you could have a 2 sigma exclusion, and then out here you wouldn't be able to learn about it. Okay? So, and that's just sort of a quick summary of the current status of the LHC. In this talk, I'm going to discuss an unusually broad set of topics for particle physics colloquium. So I want to get some guidance from somebody used to thinking about complex problems. So I'm going to get guidance from Donald. And then you might think that I mean this person, but I do not, obviously, and I don't mean this one either. So I'm going backwards in time. So Donald Rumsfeld, anybody older than me in the room knows exactly what I'm talking about, and anybody younger than me actually might not know what I'm talking about. But he was Secretary of Defense twice, including in the second Iraq invasion under George W. And in 2002, he was at a press conference where he was asked by a reporter to comment on the seeming lack of evidence being presented showing that Saddam Hussein of Iraq was providing weapons of mass destruction to terrorists. Now, any good politician, of course, if you're asked a question you don't want to answer, you just answer a different question. Hopefully I won't have to use that trick in this talk, but anyway. So instead of answering this question about weapons of mass destruction, he provided a general classification scheme of knowledge. Let me read you what he said. He said, as we know, there are known knowns. There are things we know. Okay. We also know there are known unknowns. That is to say, we know there are some things we do not know. Okay. But there are also unknown unknowns, the ones we don't know we don't know. So this is very smart, so I want to really analyze this a little more carefully. So you can obviously arrange these in a matrix, where column and row is the first or second word. So this way of arranging it makes it clear that he left out a type of knowledge, and Rumsfeld is smart, so he realized his mistake, and in 2004, we'll see, yeah, of course, the missing one, the unknown known. So in 2004, 2 years later, he wrote a memo within the Pentagon where he added the fourth type of knowledge. So there are also unknown knowns, that is to say, things that you think you know, that it turns out you did not. So that's a little more subtle. Anyway, now I'm armed with the complete Rumsfeld matrix of knowledge. He had in mind, obviously, military, but you can apply this to anything. So for this talk, I'm going to apply it to particle physics. So known would be the standard model. We have a theory of particles that describes what we see in experiments now, the standard model. Okay. Unknown known, a little more subtle, but there are cases where the standard model makes predictions for what we will see in experiment, and if we measure things precisely, we could see departures from those predictions, and that would signify new physics beyond the standard model. So this will be an unknown known. Okay. The other two are easier. Known unknown are cases where we know the standard model fails. So there are cases where we need new physics beyond the standard model. So give some examples here: dark matter, quasar matter and antimatter, inflation, neutrino mass, quantum gravity. So these are cases we know we need more. Okay, unknown unknown. Well, I'll say experimental surprises. Experiments could be running, they could see something new, and it could be unexpected. It might not fit neatly into what we were expecting, but there are cases where we could find new particle physics with experiments. So that's how I'm going to apply Rumsfeld to particle physics, and now let me be a little more specific about what I'm actually going to talk about. I'm going to give examples in each box. So for the standard model, and by the way, this is the plan for the talk, so I'm going to move entry by entry in the matrix. Okay, so for the standard model, I'm going to talk about how the LHC could measure new information about the energy dependence of interactions, which is predicting the standard model. For unknown known, I'll talk about how precise measurements at high energies at the LHC can be sensitive to new physics. So you could look for small departures from the standard model. Okay. For known unknowns, I'm going to focus on the known unknown of dark matter. Okay. And then for experimental surprises, there are many things you could put here. I'll do an example that I'm thinking about. New particle physics could distort the spectrum of the cosmic microwave background at very low energies, and I'll mention that. This part will be faster, so most of the time will be these three. Okay, so that's the plan. Applying Rumsfeld to particle physics. So first, entry of the matrix, known knowns. Okay, so things we know, which in the particle physics is the standard model. We have this amazingly successful theory of particle physics that describes the results of our laboratory experiments on Earth. There are 4 types of particles in the standard model. There's the Higgs that I mentioned already, that is spin 0 and responsible for masses of other particles. There's 2 spin 1/2 types of particles. Quarks are what are inside protons and neutrons. Leptons include the electron and heavier versions, mu and tau and neutrinos. And finally, there are force carriers that communicate forces. So there's the photon of the electromagnetic force. The other 3 communicate nuclear forces. Okay, so that's the standard model. This is what we know. And one way that we're now testing the standard model at, say, the LHC is studying the interactions of the Higgs boson, for example. So the Higgs is responsible for masses of other particles in the standard model, and it interacts with them. It's predicted to interact with them by an amount proportionally to their masses. So we can measure these interactions by producing Higgses and seeing the rate they decay to different standard model particles. And the standard model prediction that is proportional to mass would be that they should lie on this line. And we've now confirmed that it interacts with various standard model particles, and indeed confirmed that they fall on this line. So that is a spectacular success of the LHC program. And this shows the sort of precision that you're measuring these, where 1 is the predicted interaction strength in the standard model, and roughly you see that you're achieving a precision on the order of 10%, roughly, for a bunch of these interactions now.
Is this the critical test that the Higgs is the standard model Higgs?
Yes, exactly. And furthermore, if there's new physics that interacts with Higgs beyond the standard model, you can get small changes here. But qualitatively, I would say that this does confirm that.
But is it also the best piece of evidence for that at the present day?
Yes, absolutely. The key prediction is that it's a spin 0 particle that couples proportionally to masses. Okay, so this is now, and now what about the future? Okay, well this is a bit busy, so I apologize, but here, each of these there are different interactions of the Higgs, and this is showing the future fractional precision that you can measure these interactions. The gray band on the far left is the future LHC data, the remaining 95%. The other colors are proposed colliders that could study the Higgs more precisely. And I'll just note the scale is different. So here 20% is this, and this is a log scale in percent. So here 20% is up there. And just a very rough summary is that these future measurements are aiming at roughly 1%. So right now you're at 10%, and we are hoping to bring that to 1%. And that's a major goal of particle experiment in the decades to come, is to get at this 1% understanding of the Higgs and see if it still matches the standard model prediction. Okay, this is still testing known knowns. And here, the Higgs is just one way that we're testing the standard model at the LHC. We're making a bunch of different particles in the standard model. These are different particles that we're making. So the Higgs is just this part. All these other parts are not the Higgs. Here the y-axis is the cross-section, or the rate that you're making them, and it's varying over many, many decades. It's a little hard to see them, but the gray bands are the theoretical predictions. The white dots are the measurements, and then the colors are the uncertainties. And over this...
Can you repeat? Recently is 1%.
For the Higgs, presently it's sort of order 10%, depending on
10%,
the interaction.
10%,
And then a goal for the future is 1%.
Okay.
In some cases, even sub 1% with future flyers. Okay, so the Higgs is just one way we're testing the standard model, and we're testing it in many other places, and the overall summary is that it's all these measurements are matching the standard model predictions in these really diverse experimental space. And you could ask, is that enough? So have we tested it enough, or are there still qualitative things about the standard model that we haven't tested? So I'll give you an example of a qualitative thing that we haven't yet tested, but can.
Are those 1 sigma?
Yes, I think so.
Looks like it's too good.
That's actually, people have noticed, not only in this context, but also in searches for new particles, the results are systematically too good. And they're if you look at many different results, they're too good. And then there are sociological reasons that that you can explain this based on the time scale that things come out. Okay. But it's good. Okay. So I'm going to talk about something with forces. So let me just give a high-level summary of forces in particle physics, and then I'll zoom in. So there are three types of forces in the standard model: electromagnetism, the weak nuclear force that's responsible for some types of nuclear decay, the strong nuclear force that holds quarks in nuclei. There's a one-to-one mapping between forces and spin-1 particles that communicate forces. So these are the force carriers. So electromagnetism, there's the photon. For the weak nuclear force is communicated by the W and Z. The strong nuclear force is communicated by the gluon. Okay, and the strength of each of these forces is determined by a different coupling constant that we can number 1, 2, 3. So for electromagnetism, it would be the fine structure constant, and then there's an analog for each of these nuclear forces. Okay? And now a key and non-trivial prediction of particle physics and of the standard model is that the strength of these interactions depends on energy. And this shows a prediction of how they should depend on energy in a standard model. We say couplings run. This is a jargon particle physicists use just to say that they depend on energy. Our current experimental knowledge is at the far left of this plot, around, say, 100 or 1,000 GeV. So this is an extrapolation of how you would predict the strengths to operate at high energies. And here, this is 1 over alpha, and then you get these nice straight lines. So the forces are weaker at the top and stronger at the bottom. And interestingly, they all have different strengths at low energies, but this extrapolation would predict a sort of similar strength at very high energies. And that observation has led to a bold idea called grand unification, that maybe all the forces emerge from one common force at high energies. And so far, that's just an idea. We don't know if that idea is true or not. But you could ask, can we experimentally test like that these do start to depend on energy in the way that this predicts? So that's something we can ask. And this has been confirmed for the strong nuclear force, which is the one with most rapid dependence on energy. So there are a wide range of energies where it's been confirmed to depend on energy. It gets weaker with energy, including at the highest energies. These are results from the Large Hadron Collider. But interestingly, this test has not yet been done for the other two forces. So for alpha 1 and alpha 2, there's presently no experimental information about whether or not they depend on energy above about 100 GeV, the mass scale of the standard model particles. So above that scale, we have no information about their energy dependence presently. So something that I've worked on is asking, can you start to measure this with the LHC? And you can use a process called dilepton production. So this is where you collide two protons and you produce so here I pull a quark from one proton, an antiquark from the other proton. I make a lepton as antiquarkle, where the lepton here is an electron or a muon. This is an example of an event with a muon and anti-muon, where the muon, these are here, the straight lines. It's a very energetic event. Now you can organize events based on their energy, and we use a variable called invariant mass, but roughly it's the energy of the event. More technically, it's given by this equation that depends on the energy and momenta of the leptons, but roughly it's just a measure of the total energy of the event. This shows a measurement of the distribution of this invariant mass quantity, that you get this peak in the region where you're making Z bosons, but otherwise it falls. And this is a log scale, so it falls a lot. So these very high energy dilepton events are very rare compared to the low energy dilepton events. Okay, so why is this useful for measuring the strength of forces? Well, for a simple reason. The rate that you produce an event with a given value of this invariant mass depends on the alpha 1 and alpha 2 interaction strengths. Their running strengths evaluated at the mass of the event. So in principle, if you can precisely measure the shape of this distribution, it does encode information about the energy dependence of these interactions. So this I looked at with former NYU postdocs Daniel and Jameson, and we found that indeed the LHC will ultimately have the sensitivity to test this. In the standard model, it's predicted that this alpha 2 gets weaker with energy. That's a prediction that's never been tested, but the LHC, we find with the full data set, could check this fact at the 2 or 3 sigma statistical significant level, which would be sort of building evidence for it. You can imagine doing this in the future at a higher energy collider. There are proposals to build a higher energy collider with 100 TeV center mass energy, either at CERN or maybe in China, and with that, you could, with 5 sigma significance, confirm this prediction, but you could sort of build some evidence now. And here I frame this as a test of a standard model, but I do want to just mention as an aside that if you have new particles beyond the standard model through quantum effects, they change this energy dependence. So really, by measuring this energy dependence, you can also learn about whether or not new particles are present, but even as a test of the standard model, you can start to do interesting things. Okay? So that concludes what I want to say about this entry of the Rumsfeld matrix, and I'd like to now move to another entry of the matrix. unknown knowns. So new physics modifies known physics. And here I mean cases where the standard model makes a specific prediction for what you should measure, but there's some situations where we could look for departures that would then be a clue for new particle physics. And I'm going to again talk about dileptons. We don't yet have much information about these rare high energy dilepton events, so that's a case where by measuring it more precisely with more data, we could in principle look for departures, and it's a case where there could still be dragons. So that's sort of the way that the unknown known would manifest here. So I'm going to apply this philosophy to a specific idea, and it's very important in particle physics that we call effective field theory, and for anybody who's taken my particle physics class, this is kind of a core idea, but roughly it's that at the more fundamental high energies, we might have there might be some unknown complete theory that describes things, but at low energies in experiments, we have access to what we call the infrared theory, which is a coarse-grained description. And the reason this is useful is that a finite number of these IR theories can capture the effects in experiments of an infinite number of UV theories. So a little more specifically, you can organize states in the standard model by their mass or energy, and so the masses here are kind of characteristic of the mass of the Higgs. There could be some unknown heavy physics whose form we don't know and maybe haven't yet been able to access with experiment. So in practice, what we can do is form an effective theory that captures the effects of the heavy physics at low energies, and we do that by defining a cutoff scale between these different states, set by some energy scale lambda, and we can add new interactions to the standard model that capture the effects of these new heavy things. And the way that those new interactions will affect things parametrically has a very simple behavior that follows just from dimensional analysis. If I set lambda to infinity, the effects go away, and then it should be, just by dimensional analysis, it should go like the energy scale of the experiment over that scale lambda to some positive power, so that you get this decoupling behavior. This is going to be important. This is going to be important for what I'm going to say in a moment, but this is a way to estimate the size of the effects of the heavy physics on these new interactions that you add. It should scale roughly like that. Okay. And there's a long history in particle physics of using this concept of low energy interactions to look for new heavy stuff. So just as one interesting example, the Gargamel experiment, which was done at CERN, it was a beam of neutrinos is passed through a bubble chamber, and it found evidence for new interactions that were not yet seen. So in this is a famous event. This is a paper about one event, which you could do back then, I guess. So it's evidence for new interaction. In this case, it's a neutrino interacting with an electron. So the neutrino comes in, it kicks an electron in the material, and then you see it. So can anybody see the electron in the image? It's that one. So it's coming out like that. It's one of the most famous. It's probably the most famous electron in history as far as a single electron. But so this was evidence for new interaction that hadn't been seen, and there's other evidence I'm not showing, but this together built the evidence for the Z boson, which generates this interaction. But at low energies, it can be captured just by adding a new interaction between neutrinos and electrons, which was the first evidence for the Z, and this was before we had experiments that could directly make Zs, which later we were able to do and confirm it. But we first knew it was there by the effect of these interactions at lower energies. So this is the type of philosophy I want to now apply at the LHC. So I'm going to look at the effects of new physics on the force carriers, and specifically the photon ZW. And the leading effects can be captured by adding to standard model 4 interactions that I kind of show here as cartoons that I can label S, T, W, Y. Okay? And all 4 of these interactions affect dilepton production. So all 4 of them affect it in this peak region where you're making Z bosons. The W and Y lead to a high energy effect, which can either add or subtract from the expectation of the standard model, and by an amount that parametrically goes like this energy squared over lambda squared that I mentioned. Now, before our work on this, the conventional view was that the best way to constrain all 4 of these interactions is with ultra-precise measurements that were done in the past with electron-positron colliders making Z bosons. But looking at this cartoon makes it clear there's sort of 2 options. You could shrink the error bars and go for very small effects, or you could try to go out to these rare high energy events where you start to get effects that are fractionally bigger. So there's an interplay between looking for rare high energy things or shrinking error bars. And we realized a very simple numerical argument, which is going to be embarrassingly simple to describe, but it wasn't new in this context. So the new physics effects grow like energy squared over lambda squared. The kind of historical measurements that were viewed to be the best for these are They have 10 to the minus 3 precision, so ultra-precise electron-positron collider measurements. Add energies around the Z mass, which is about 0.1 TeV, where TeV is 1,000 GeV. But given this energy growth, then obviously you can beat these historic measurements if you can perform measurements in a hadron collider with 10% precision at energies above 1 TeV. All right, and then just by the scaling argument, you'd be better. The non-trivial thing is that we showed in cases of interest you can achieve this precision. So that was in this work with former MB postdoc Duccio and others. So we looked at dilepton production, which is affected by these new interactions, same process I used before to look for the running couplings. And we looked at single lepton production. So in the case of dilepton production, you're measuring invariant masses before. In the case of single lepton production, you measure the momentum of this lepton. So you're also making a neutrino that you don't measure, but you can measure this momentum. And in both cases, these are affected a little bit by these new interactions. Okay? And I'll now jump to the punchline. So here's the punchline. So here, the x-axis is the strength of this W interaction. The y-axis is the strength of this interaction using a dimensionless measure of strength where 0 is no interaction, so standard model is 0, 0. The thing that had been viewed as the best way to measure these, the old electron-positron collider bounds, are this gray region. And what we showed is that the LHC, by measuring dileptons, can constrain it to be within this purple ellipse, and by measuring single leptons, can constrain it to be within this green vertical band. And you can see it's much better than the Z measurements, and it's just taking advantage of that simple scaling I said that you can in practice do better than 10% above 1 TeV. In terms of the mass scale of the new physics you're sensitive to, you can be sensitive to physics of the 10 or 20 TeV scale using these measurements, which would be much too heavy physics to make directly.
Is there a sensitivity to the interactions with quarks and the gluons and the higher order in QCD that is a problem with this?
Well, so Drell-Yan is computed to ultra-high precision in the standard model to next to leading order QCD, and that's kind of key between why there's enough theoretical precision to look for these effects. So in terms of the new physics effect, you can estimate sensitivity by looking at it in leading order.
I understand.
The Adanalo correction.
No, I was asking about that.
The Adanalo correction to the new physics just shifts the value by order 10% or less. So here we're doing leading order, and we're still working on the analog. But that, if you want to ask the reach, you care much more about the precision on the standard model.
Yes, that's what I was asking about.
Oh, next to leading order. Yeah, so it's sort of percent level. So we're comparing to differential next to leading order predictions, and PDF uncertainty, and we're doing a careful fit to get these. We didn't have to calculate that, of course, so there's tools that one can use to show that precision. Okay. So that's now, and the cool thing about this technique is you can extrapolate it to higher energy. So in principle, you can imagine in the future doing this at 100 TeV collider, and the entire plot on the right is contained within the red box on the left, so that's even much better. And you're getting to these amazing scales of order 100 TeV of physics. And after we noticed this has become one of the motivating selling points for such a collider. Also, the running coupling measurements I mentioned before. Okay. So that's sort of a practical example of some work. I'll just give one quick slide on philosophy/workflow, but so there's a big field. There are many experimentalists working on high energy particle physics, so it's hard to have impact just by writing theory papers, and really us theorists don't really matter. It's really an experimental enterprise. So how can the theorists help? Well, it helps to really work with experimentalists in some cases to get it across. So ways that I've tried to break that barrier, I've collaborated with Atlas on now 3 different searches for speculative new particles, where I helped them understand what their effects would be, or to simulate those effects. We're working on white papers, which sort of as service. So an example of what's happening right now is Europe has a 5-year strategy cycle called the European strategy. So right now they're charting the next 5 years of CERN, and so I've contributed to white papers to go into that strategy, and we'll see in a few months what they say. And finally, community events. So just as an example, I'm running an 11-week workshop at KATP in 2021. They plan things far ahead. About exactly the type of stuff I've been talking about. So using precision measurements at the LHC of standard model processes to look for new physics. So Kyle's one of our advisors of that, and we're going to get together experts on new physics with experts on precise standard model calculations and see if there are more examples that we can find of this approach working. Okay, so that's just some ways of going with communities connecting. Okay, so I finished the unknown known box, and now I'm ready for a new entry of the Rumsfeld matrix. And things are going to shift a bit because I've been so far in this talk focused on high energy collider physics, and things are going to migrate to be more cosmological. Okay, so no new physics. And there are a bunch of cases where we know the standard model fails. And here I've put a bunch of them in circles. I've put solid circles around cases where we really seem to need new dynamics, and dashed lines are in cases where we have a theoretical argument for expecting new dynamics that we would call fine-tuning. Each of these is super interesting and could easily be an hour colloquium. So I'm going to choose one circle that I've been particularly interested in recently, which is dark matter. But these are all cases where we know the standard model is inadequate, so it's a known unknown to Donald. Okay. So we have, as you've surely seen, this now precise understanding of the energy budget of our universe, the composition. All of ordinary matter and periodic table and physics departments is within this 5%. It's mostly dark energy, 70%, that's driving the accelerated expansion, and then most of the matter is dark matter, which is some unknown matter that's most of the matter in galaxies. So how do we arrive at these 1% numbers that we have now? Well, the main tool has been the cosmic microwave background. So this is the radiation left over from when the first atoms formed. And it's a black body that now has a temperature of 2.7 Kelvin. We can form its power spectrum, shown here. Okay? And then this video shows how the shape of the power spectrum would change if you, for example, vary the size of this slice of dark matter. And if you watch carefully, the relative height of the first and third peaks is very sensitive to the amount of dark matter. So that's in practice how we really get these percent level numbers nowadays, is precise things like this. But I'll now give maybe a more intuitive way of understanding dark matter. That's not where we get these precise extractions, but this is very visual, is, for example, looking at clusters of many galaxies. So this is the famous bull cluster image that I'm sure a majority of you have seen many times. But so here the green contours show the location of most of the mass from lensing of more distant objects. With the colors, the red and blue, shows the location of the ordinary matter, which is mostly gas in the cluster emitting X-rays. And you can see that the ordinary matter and most of the matter are in different locations. So that's sort of visual evidence for the dark matter. And the way we interpret this image is that these two clusters, we're looking at it after they've merged, and the dark matter is passing through unperturbed, whereas the ordinary matter is interacting and then displaced from the center of the clusters. That's what you get, this displacement. Glance mentioned that NYU has been involved in some of these simulations of that merger. But so really it's a CMB where we get their 1%, but that's kind of harder to intuit. So it's fun to just have something you can look at and say, okay, I see the dark matter. Okay, but I'm a particle physicist, so I want to understand what it's made of. And if it's made of new particles, they should have several properties. They should be stable on cosmological timescales. They were made in the early universe, they're around now. They should be electrically neutral, so that they're dark, or at least to a good approximation. And they should have been non-relativistic when galaxies form, so that you form the amount of galaxies we see to have formed. And no single particle, as a single particle in the standard model, has these three properties simultaneously. So therefore, it can't be explained within the standard model, and it calls for new particle physics. There are a couple of interesting caveats to this implication. And I blamed some of our NYU colleagues. You can ask more about those caveats, but up to those caveats, it requires a new particle beyond the standard model. The caveats all involve collections of particles, where you try to make the collection of particles have those three properties. Okay? So we have the standard model, and up to the caveats, we want to add some new particle beyond the standard model, which would be the dark matter particle. And then you can ask what are possibilities for what this could be that would potentially explain what we see. The community favorite has been the weakly interacting massive particle, or WIMP. So I'm going to kind of describe to you the story of the WIMP, and then I'll talk about some of my own work on ideas that go beyond the WIMP. But first, I'll review the WIMP. It's the idea that the dark matter has rapid interactions. There are interactions that can change the number of dark matter. So two dark matter can find each other and annihilate, for example, into ordinary matter. The inverse process can also happen. And therefore, you would begin in the universe with many dark matter, the comparable number of dark matter and photons. Okay, now I'm going to give you sort of a cartoon understanding of what happens, and then I'll make it a little more refined in a moment. But just as a cartoon, you can imagine in the early universe placing a box, and it has a bunch of dark matter in it. And now as the temperature drops below the dark matter mass, these annihilations will rapidly remove it. So if these red dots are the dark matter particles, then the number of them dilutes as the universe cools. And then something happens we call freeze out. When the annihilation rate is slower than the expansion of the universe, then the number in the box are going to be locked, and that should match what we see today. So this cartoon I just showed you was not accurate in one very important way. The universe is expanding, so let me make a more accurate cartoon. Well, yeah, so the volume of the box really should grow as temperature to the -3 as the universe cools and expands. So you can more accurately start with a small box, which has a high density of dark matter, and then as the universe expands and cools, the box is both growing and becoming more dilute at the same time until you arrive at the freeze out. So that was a more accurate cartoon. And now I'm going to make this even more accurate by showing a plot. So here I plot the amount of dark matter, where the y-axis is its number density times the volume of that expanding box. And here the x-axis is time from left to right, measured as inverse temperature, because the temperature cools as time progresses. When it turns non-relativistic, the number density falls exponentially as a function of temperature. This is just a consequence of the Boltzmann distribution. And if it were to fall exponentially for a long time, there'd be nothing left. But in practice, fortunately, what happens is that these annihilations become slower than the expansion rate. So in reality, it'll fall exponentially following the red curve until the freeze-out moment, and then it'll jump on to one of these blue curves. The larger the cross-section, the more depletion you can have before the annihilation rate becomes slower than the expansion, and therefore, if you raise the cross-section, you go down these blue curves. And therefore, there's a one-to-one correspondence between the cross-section and the energy of dark matter we see today, and you can choose the cross-section that matches the amount of dark matter we have today. And if you do that, you get this number, 3 times 10 to the 26 centimeter cubed per second. So that's sort of in ordinary units. In particle physics, though, cross-sections, we write them as interaction strengths divided by mass scales. So the way a particle physicist might write this number is the following. Here I'm choosing alpha E and M as an example interaction strength, but I want to stress it's just an example because the dark matter is dark, it's not electrically charged, but if it has an interaction strength characteristic of electromagnetism, you would have an alpha E and M squared here, and then the mass scale that would give you this number is 200 GeV. And this is a very interesting number to a particle physicist because within a factor of 2, it's the mass of the Higgs, and it, in general, is the characteristic mass scale of particles in the Standard Model. And this observation is miraculous. We call it the Witten miracle. Because a priori, this cosmological argument doesn't know anything about the scales of particle physics. It just knows about the amount of dark matter we have and the Hubble expansion. But then you find that the cross-section that would match the amount of dark matter we see is characteristic of a mass scale that appears anyway in particle physics. So this we call the Witten miracle. There's 2 possible interpretations of this fact. So the optimist interpretation is that this is a clue that dark matter has something to do with the Standard Model of particle physics and the mass scale there. The pessimistic interpretation would be that it's just a coincidence and a red herring, and we don't know which of these 2 interpretations is true. But in practice, this has driven a lot of the work in the field, the optimistic read of this. Okay? But suppose I want to be agnostic, and I want to just allow for, maybe I don't want to take that too seriously, so what if I just allow for a wide range of masses? Then we could ask, what are the possible masses? And for this type of thermal dark matter candidate, there's an upper bound on the mass that we call the unitarity bound, and this is just because if you make the mass larger, the cross-section gets smaller, and at some point it's too small to dilute it, and you'd have too much dark matter today. So that gives an upper bound on the mass of about 300 TeV. There's also a lower bound on the mass for these type of thermal dark matter that comes from the requirement I mentioned before that dark matter should be non-relativistic when galaxies formed. So this is an example of a simulation, and on the left, the mass is much heavier than 1 keV, and it really is very non-relativistic when galaxies formed. On the right, the mass is 1 keV, and you can see there's a lot less structure. So what happens is that as you lower the mass, you remove structure, and this is sort of the critical scale is around 1 keV, and the simulation on the right is about the limit of the amount of structure that you can afford to remove before you would remove too much. So roughly, there's a lower bound of about 1 keV, beyond which it would be too warm and not match what we see for structure today. So there's still a very wide range of masses that would work between 1 keV and a few hundred TeV. For these type of thermal relic dark matter, for the experts will know there are non-thermal types of dark matter that can have a much larger mass range, but for these type of dark matter with rapid interactions, you get this range of 1 keV to a few hundred TeV.
Can you say just a word or 2 more about what the unitarity bound has to do with unitarity?
Can I say more in a moment? Because it'll be more clear in a second, but it's going to be
Fine.
the maximum interaction strength. So wait one slide. I want to ask what models can live these different masses, and I want to add one more axis that answers Alex' question. I want to add an axis to this plot, which is interaction strength. And now I want to consider the two-dimensional interaction strength mass plane. Okay, and in this plane, the 2 warm is really a limit on mass. The unitarity bound is actually a limit on coupling, and it's the maximum coupling that things can have is 4 pi, beyond which it's strongly coupled. Okay, so WIMPs are just a little localized part of this bigger phase diagram that we can imagine. Now, part of this phase diagram is actually already excluded by things I've told you already. I mentioned, for example, cluster mergers, and the way we interpret it is that the dark matter just passes through unperturbed and the ordinary matter interacts and gets stripped out. And roughly speaking, that says that dark matter interaction should be weaker than ordinary matter interactions, and that would not be true in this brown region where dark matter would self-interact too much. So dark matter cannot live deep in this brown region for cluster mergers to look like this. The edge of the brown and white region is very interesting because then you could have astrophysical effects that would be observable of the self-interactions, and there's a whole community looking for those effects on dark matter halos and clusters. So the edge is really interesting. There are even people that think it's favored. I'm more agnostic, but anyway, deep in here is not allowed. Edge is interesting. Okay, so now I want to ask what other models can populate more of this phase space. Okay, and there's sort of a class of models which appeared in various forms a bit over a decade ago. Neil here was one of the pioneers. It's the idea that dark matter, instead of annihilating through interactions of the standard model, could annihilate through some other, say, dark interactions. If dark matter is part of some hidden sector, it might annihilate into states that themselves are not known particles, and then through some new dynamics. And then the strength of this interaction is a priori undetermined. So I can write, say, alpha dark over m squared. And the key point is this alpha dark could in principle be much smaller than the known interactions. And really the argument I gave before just constrained the ratio. So if alpha dark is smaller, m can be smaller. And in this phase diagram, this would point to a line. So everywhere along this line, the cross-section is the size you would want. But the mass actually is not determined by this argument if you're agnostic about the interaction strength. For those of you who were here earlier in the semester paying careful attention, Jonathan Fang gave an excellent colloquium where he presented exactly this phase diagram in this line, and he called this line preferred. And then he described an experiment he's working on phaser that's targeting the lower part of this line. But this was sort of the community view, especially say 5 to 10 years ago after the realization that you could go down this line. It was that this line would be preferred. So some of my work has been identifying models off this line. With apologies to Jonathan. So one possibility is that dark matter could annihilate to heavier states. It was actually implicitly sort of assumed in my prior discussion that dark matter is annihilating something lighter, and that's normally what people assume. And if 2 dark matter particles are at rest when they annihilate, then conservation of energy tells you they can only annihilate to something lighter. But in the early universe, it has a temperature and a kinetic energy, and occasionally 2 dark matter will collide with enough kinetic energy to make something heavier. So this is, as a technical possibility, was observed a long time ago in the early 90s. It didn't receive much attention as an application into models. So a few years ago, myself and my collaborator Raffaele sort of revived this and showed the implication of this idea for this phase diagram I was just showing. In this case, you need to be careful about the fact that things have a temperature, and you need to perform a temperature average of the cross-section. But if you're careful, you find the following. You get the usual form of a cross-section, alpha squared over m squared, like before, but you get this exponential that depends on the mass splitting and the temperature, and this exponential comes from Boltzmann, and it's just measuring the fraction of dark matter with enough kinetic energy to make these states. So it has a simple to understand origin. And then this whole quantity should have the same size as before, that's characteristic of WIMPs. But the key point is this exponential can be a very small number, and therefore, keeping alpha large, if the exponential becomes small, the mass can become small. So this points to a different region in the phase diagram. And I just mentioned also more ongoing work developing models of this type with a bunch of NYU students, Dee, Christina.
Does that mess up the kinetic energy distribution of the dark matter that survives?
It's still going to be Maxwell-Boltzmann. It's not going to be different. But, and for the kind of heavy type of dark matter I'm talking about, it is very cold. So it doesn't matter. But if you ask that question again for the next type of dark matter model, there's a more interesting answer. So back to the phase diagram, so if I hold alpha fixed, it goes to lower masses, so it lives above this ultra-weak line from before. Right, so if I keep alpha fixed, if the exponential becomes small, I lower m, so I move to the left. And interestingly, this goes right up against the self-interaction, so the models here at the edge are interesting astrophysically. because you can now have large self-interactions. Okay. So next I want to ask, what about below the line?
So what you call forbidden was previously forbidden, but you're saying...
Oh, no. The name is from this Greisten-Seckel paper, and they just pointed out the technical possibility that you should consider annihilations to heavier things, and they call it a forbidden channel.
Right. So not, like you're saying it's not forbidden.
It's forbidden at 0 temperature,
Right.
but at finite temperature it's not forbidden, but exponentially suppressed.
But it should actually be called allowed in terms of the parameter space.
Yeah, I agree.
Just to make sure
I was paying
people
respect to
understand
the
that.
history of the technical observation. We can call it allowed dark
Oh,
matter, right?
I'm sure Rumsfeld would love that.
Yeah.
The allowed forbidden. Sorry about that.
Okay.
You invited it.
I did. Bring it. Okay. Okay, good. So now I want to go below. Spoiler, I can do that too. Okay, so suppose the annihilation rate is too small, so in the lower region. Suppose that this is too slow. That means you have too much dark matter. So then you can ask, are there other interactions besides annihilation that can remove the dark matter, and that would let us recover this part of the parameter space. In particle physics, given any interaction shown by some diagram like this, you can generate a new interaction by rotating it. It's a general statement. So if I rotate this diagram, I generate a new interaction. This can be very rapid because there can be a lot of x's, but it doesn't change the amount of dark matter because one is in and one is out. So that's actually not relevant for setting the amount of dark matter. So we had a simple idea that you can use the fact that something like this can be rapid and just change the identity of the thing coming out. So you could set the dark matter abundance instead of through annihilations through inelastic scattering. If you want this to be stable, then this should be heavier because whichever is heavier by this diagram can decay to whichever is lighter. So here it's inelastically upscattering into some heavier state. Okay, so let's think about this a little more carefully. So this diagram lets me change the dark matter into this other thing that I'm calling a dark partner. But that alone doesn't really tell me I'm removing dark matter. It's just telling me that these can go back and forth. So to conclude that I'm removing dark matter, I need to add some interaction that removes this. And that could be its own rapid annihilations in principle. So the combination of these two processes removes dark matter, where the process on the left changes dark matter to dark partner, and the process on the right removes dark partner. And then if both are active, you can remove dark matter, and then that's now an alternative to annihilations. I guess this we highlighted in this paper here. If either of these processes stop, then you set the amount of dark matter. So we call co-scattering the case where the diagram on the left stops first. I'll just point out as an aside, another possibility is the diagram on the right stopping first, and that I studied with Christina and Pojan, but I'm not going to talk about that more now. I'll just say that's a possibility. You can ask me later. I'm going to focus on the case where the diagram on the left stops first. And so when we thought of this, we thought it was completely new, but I've learned in life when you think you thought of something completely new, a more senior person down the hall probably has thought about it before, and that was true here. That this had appeared in the mid-90s in a paper by Glennis and Rocky, where the dark matter is scattering against a pion into a heavier state called an R hadron. It's a composite state that contains a gluino inside of it. So Glennis had a program at the time looking at the possibility this gluino could have a mass around a G, which was allowed at the time, and it's not allowed anymore. So this idea is now excluded by high-energy colliders. And just for fun, I'm pointing out the second paper is not about dark matter, but it's on the same topic of GeV gluinos, and some trivia is that it's one of the first papers written by our current dean of science. But anyway, this idea was excluded by colliders. So really, our observation was that the mechanism is more general. It can be applied to other models that are still viable now. So for example, we can replace the pion with an electron, and we could, well, not take this to be a gluino, but just some particle that's not charged under standard model gauge interactions. So we studied the phenomenology of this in a recent paper. So let me just talk about the rates of annihilation versus scattering in this model. So for annihilation, which would be the old way of doing it, the rate of annihilation goes, well, as the cross-section, so it's alpha squared over m squared, but also as a number density, because from the perspective of a dark matter particle, you need to find another dark matter particle to annihilate with. So you get this factor of number density. So this co-scattering is completely different now, because if I'm a dark matter particle, I need to find an electron to scatter against. So now I have the electron number density here. And this is, if the temperature is below the dark matter mass, this is an exponentially important distinction, because there can be exponentially more electrons than dark matter, and that enhances the rate of the diagram on the right by an exponentially large factor, which allows alpha dark to be exponentially smaller. So if we go back to our phase diagram, the fact that we can take advantage of this large electron number density to remove dark matter lets us move down in the phase diagram and contemplate models with much smaller interaction strength. So I've now succeeded in claiming the whole phase diagram.
Question.
Yeah.
Could the partner particle be unstable?
Yeah, the partner particle is unstable because the exchange diagram causes it to decay back.
I mean, it's just decay. I saw you annihilate with it, so.
Oh yeah, I'm using annihilation to remove it
Yes.
because the decay goes back to the dark matter. So the decay by itself doesn't set the common chemical potential to 0. So you need some other. So just this decay is not sufficient to remove dark matter. You need something that really removes it. But indeed, it does decay as a consequence of this diagram back to here.
I see.
Yeah, kind of a technical answer is if you have a Z2 breaking decay, then it would cause the dark matter itself to be unstable, which is why annihilation is a better way to remove it. But we can talk more later if you want. Okay, so bottom of the phase diagram. So now let me just very practically.
That diagram, why are you cutting off? You're cutting off at a mass here on the far side, the heavy mass. Like, is that just because you ran out of space on your slide?
No, you run into this unitarity bound. So typically, the interactions are not going to be rapid enough to
Because
remove
you
it.
have to be. I see. You have to be below. You have to go down from the unitarity bound.
Yeah, and you could ask why does this model hit the unitarity bound,
I see.
and there's a unitarity bound on the partner
Of course,
that kicks
yes.
in. So in both cases, these types of models I'm talking about run into these
They can't
unitarity
go to
bounds.
arbitrary high masses.
There are other ideas where you can get around those. You can ask our postdoc Asher, for example, where you make the dark matter unstable. Or you can talk about later, but at least in this class of models, you have this unitary bound.
How does this whole phase diagram depend on temperature?
Well, for the whole diagram, it's a thermal relic, so the temperature starts above the dark matter mass. Here I'm not showing the temperature because there's a history you should imagine for each point in the phase diagram. So for any model in the phase diagram, the temperature starts above the dark matter mass and then drops below the dark matter mass, and then these interactions freeze it out. So there's sort of a history that you have to think about for each point, but this is just talking about the 0 temperature properties.
0 temperature properties
Correct.
prepared by temperature changing protocol as you described.
Yeah. So in each case, you throw this into our expanding universe, and the temperature will scan through a bunch of values. In each case, the dark matter abundance then is set right after dark matter turns non-relativistic, because that's when the Boltzmann suppressions kick in. So it all happens at about the same time, actually, kind of universally across all of these models. When the temperature is about 5 or 10% of the dark matter mass is when you lock it in, kind of universally in this diagram.
But Shura's question opens up another thing, which is that he called it a protocol. Like, the universe has given a temperature protocol to this experiment, and are we extremely confident about the temperature
No.
protocol at these high temperatures?
That's a very good question. So here I'm assuming sort of the vanilla assumption of a radiation-dominated universe up to some temperature above the dark matter mass. If you allow for other things to happen, which could have, like a process that creates a lot of entropy, can dilute the amount of dark matter, and that's a way to move to the right here. It's sort of another axis, but indeed I'm making sort of the simplest cosmological assumption. If you allow for some process that dumps in a lot of entropy, then you can dilute dark matter, and then that lets you move to there, for example. So indeed, once you start playing with cosmology dials, there are other options. And here I'm playing with the particle physics dials, assuming the simplest cosmology, and it's an assumption.
And cosmology dials is a protocol how you cool down your temperature.
Yeah, exactly. And all we really have experimental information about is up to a temperature of about 1 MeV from big bang nucleosynthesis, measurements of element abundances. So to go above that, you're extrapolating.
Okay.
And that's why these questions are good, and you can make other assumptions, you can make more complex assumptions about that extrapolation, and that can point to different models. So indeed, that was an implicit assumption throughout this discussion. Thank you. Okay, so I want to practically ask the implication of these models for experiments where I'm coupling two electrons. So here, this is the dark matter mass. This is the rate that the dark matter would scatter against electrons. Along this orange-yellow line, just the vanilla annihilations would have the right amount to give you the right amount of dark matter. And then this co-scattering idea lives down to the blue line. And in fact, it can go anywhere between them, but that's the lowest it can go. And then the amount you're moving down is just the ratio of electron to dark matter number densities, that exponential factor. And this is a log plot, so it's a very important, experimentalist cares about 4 orders of magnitude coupling. Okay, so here's the current experimental constraints. They're shaded in gray. I'm not going to explain all of them in all time now, but I'll just mention this one here, for example. So here we're actually assuming dark matter couples to electromagnetic current, which means it also couples to protons. So in this region, you would see it in what's called direct detection experiments, where you have big clean tanks, and you're looking for dark matter depositing energy, and it would deposit too much energy in the shaded area. The whole white area is presently allowed. Part of the WIMP curve is allowed. The whole post-scattering curve is allowed. And now I can show you some projections for future experiments in this plane. So here's two experiments that it seems will happen. Sensei is an experiment, unlike these that are looking for dark matter scattering against protons. This is an experiment that looks for dark matter scattering against electrons, and you can go to lower mass. It's a silicon detector using a new technology called Skipper CCD, and it's been funded and should happen. This purple curve is an electron-positron collider in Japan, whose intended purpose is to study bottom quarks, but it could also make dark matter, and this model would above the purple line. And you can see a combination of these. So these two experiments are sensitive to everything above these lines, and they would completely cover the vanilla annihilations case. So if dark matter in this part of the primary space is annihilating into electron and positron, we will see it soon, in the next few years. But you do not have a sensitivity to cover the whole region where the inelastic scattering is working. So it's an important distinction. Now, there is a lot of effort now going into this plane and a lot of new ideas and creative ideas. And I'll just highlight one thing. This is an idea by Dan McKinsey's group in Berkeley of using detectors made of superfluid helium, and they're looking again for dark matter scattering against protons. And they claim to imagine technologies where you can go to much lower energy deposition than current technology allows. This still needs R&D, but anyway, at least they imagine being able to get down to a point where you would really cover this co-scattering model. So just to point out, this model is interesting for kind of big ideas people have, but these two will happen. And this needs more R&D, so I don't want you to look at weigh them the same. Okay.
But isn't the dark partner easier? Because if the dark partner annihilates fast, isn't it also easy to produce?
Well, good question. Here I'm taking that sort of pessimistic assumption that the dark partner is annihilating into dark states, because there's no need for it to annihilate into us.
Oh.
And then you need to go after the electron coupling. Indeed, if you do annihilate into E plus, E minus, it is easier to produce than that.
Fine, yeah.
So you're right. There's another interesting thing. Here in this region, the dark partner, it decays late enough that it would distort the CMB. So there can be astrophysical signals of that decay, depending on the lifetime. Okay. Almost done. Any more questions there? Okay, so I'm up to the last box, but this box is quick, so don't worry. I'm not going to delay wine too much, because really, I know unknowns. What do we really know? So, for this talk, this is experimental surprises. Experiments are running. They could find new particles that might surprise us. So Rumsfeld called this things we don't know. And he gave some wise advice, actually, about how to approach unknown unknowns. So I'll give you a quote, a Rumsfeld quote. He said, you can only know more about those things by imagining what they might be. Because you don't know what you don't know, but you can try to imagine what do I not know. So as a theorist, you can, given experiments that are running, you can imagine hypothetical particles that they could see. And you should imagine things that are not excluded by other experiments, and that's actually not that easy. But that's something we do a lot, is given things that are happening, we ask, what can I imagine that they could see? So I think Rumsfeld would be happy with this approach. So just as an example of this, the cosmic microwave background, I mentioned before, it's the black body of photons left over from when the first atoms formed. Here the x-axis is photon energy normalized to temperature. The y-axis is number of photons. We've confirmed that it's a black body to spectacular precision at some energies. So Fire-S is a component of the COBE satellite. The error bars here, in some cases, are much smaller than 1 part per thousand. I think approaching a few parts per 100,000. This is a balloon experiment with sort of 1% precision. And then there are a couple of other ones, little energies I'm not showing here, but this is sort of illustrative of the range of energies that have been measured. And what I want to emphasize is that we've actually although we have this spectacular precision at some energies, we haven't measured it at other energies. So where I'm drawing a black line is just an extrapolation of the prediction of a black body, but it's actually never been checked. We haven't figured out a way to check it by experiment yet here or here. So that's just a theoretical extrapolation. So this is a case where I can imagine, as Rumsfeld would say something, unknowns. There could be dragons, for example, at low energy, where we haven't yet measured it. So if we can figure out ways to measure the low energy part, that's a place where we could potentially look for the effects of new physics that might have changed the low energy part. So I've been working on a class of models that would be interesting here. There's a new photon that we call a dark photon. That's not our photon, but some hidden sector photon. And if in the early universe we know that there was a bath of photons, if you also have some dark photons in the early universe, then they can oscillate into ordinary photons. It's analogous to neutrino oscillations for those who know about that, and that can then change the spectrum of the CMB. So here the photons you inject have an endpoint, which is why this ends. So the new particle physics is adding to the spectrum this red part, and then it is not changing the spectrum at all at the well-measured energies, but it becomes the dominant source of photons at the very lowest energies. So that's a possibility where the spectrum could be very different, and if we can measure it at low energies, we can test whether something like that happened. So that's an example of a dragon. So there's an emerging experimental field in cosmology called 21 centimeter cosmology. It's still mainly futuristic. A bunch of experiments are going after this, and it's sensitive to this part of the spectrum that's deep in the unmeasured region. So when these experiments can test this type of particle physics, and since I'm basically out of time, I'm not going to go through this slide at pedagogical speed, so you can ask me more after, but I'll just kind of more as a quick advertisement. There are experiments targeting this 21 centimeter absorption or emission at the epoch when the universe is a few hundred million years old. You have clouds of hydrogen gas. 21 centimeters hyperfine splitting in the hydrogen atom, so you can absorb or emit photons of wavelength 21 centimeter. The dominant source at this epoch of those photons is the CMB at these low unmeasured energies. So if new particle, and then then you measure it. So there are radio antennas today that are then looking for these photons, and you can see sort of how this gas affects their spectrum. So if new particle physics is injecting more 21 centimeter photons, then these experiments, these cosmology experiments, could also test this new particle physics. So that's sort of the idea in this paper, and I have ongoing work with a bunch of NYU people on more ways to test these very soft photon injections. Just to advertise, there's like a very tenuous claimed first detection of these 21 centimeter photons, but it's published in Nature, so it must be wrong. But they claim to see absorption this deep. That's impossible in the standard cosmology, which is the green curve, and if you do add more photons, you can get a deeper absorption. It's a very hard measurement, so I don't think anybody believes it at this stage, but it is sort of at least showing an emerging field, and there are a bunch of other experiments now targeting that, and those experiments would test this type of particle physics, but I don't want to oversell the anomaly. Okay, so this was topically a broad talk on particle physics. It was organized around the Rumsfeld matrix. He had in mind military, you can apply it to anything, so as homework you can try to apply this to your own domain. But here I applied it to particle physics. So known knowns are things we know. We have the standard model, but there are still aspects of the standard model that haven't been tested. So here I highlighted one that I've worked on, which is the standard model predicts an energy dependence of interactions, which mainly hasn't been tested yet, and the LHC and beyond can start to test some of these in the case of the energy dependence of the weak interactions. Okay. Unknown knowns are things that we think we know but don't, and the standard model makes specific calculable predictions for some experiments, and departures from that could be evidence of new physics. So the application here was I showed how the LHC can look for new interactions that affect the force carriers, and before our work it was believed electron-positron colliders with ultra-precise measurements of Z bosons were the best way to look for these, but we showed that the LHC can do much better. Okay, known unknowns are cases we know the standard model fails, and one example is dark matter, and I highlighted this phase diagram to organize the discussion on different ways dark matter can be produced. Say more than 10 years ago we knew dark matter was on the green, in this green region. 5 years ago we knew it was along this line, and I've shown you sort of simple theoretical changes, simple deformations from the particle physics point of view to the assumptions that underlie the Wimp miracle that can populate a lot more of this phase diagram. Okay, and unknown unknowns we don't know, but that would be experimental surprises, and I showed one example that the low energy frontier of the CMB could be a place to look for dragons, and it's sort of the opposite energy scales. So here I'm looking for new particle physics at the highest energies, and in here I'm looking for new particle physics at the lowest energies, but they're both places where Rumsfeld would imagine that it could be. So. And let me just say, a bunch of experiments are coming where unknown unknowns could appear. So here I just highlight some of the experiments in the next few years that I'm most interested in. Thank you.
Questions for Josh?
Always a pleasure. It's dangerous to mess with the photon in the sense that we know the universe is exceedingly transparent at all wavelengths. For instance, you can see radio sources at long wavelengths to very large distance. Does messing with the photon sector affect the transparency or brightness of long?
Good question. The photons of certain, so dark photons of certain energies are very dangerous because they mess with photons. But dark photons respect a very simple decoupling argument, which makes them very safe at very low masses, which is if the mass of the dark photon is much lighter than the energy of the relevant energy of the experiment, then there's only one linear combination of photon and dark photon that is the photon, and the other one decouples. So for that reason, if a very, very light dark photon sort of changes nothing to the leading order, and for the model that I was considering, it was in that regime, in this decoupling regime from the point of view of the experiments you're talking about, and then these cosmic oscillations end up being the leading effect because they can go through resonance that can enhance it. But so dark photons are special among light particles that they, when very light, can actually have a surprisingly large interaction strength with us and be safe because of this decoupling.
So meaning that like a high redshift radio source that we see is producing, it's producing at its source photons, but they propagate to us as this photon dark photon.
Well, it's producing. It depends. Yeah, it depends on what scale. It's producing the interacting state. Yeah, and then you need to be careful about how that scale compares to the mass.
Yeah.
But if the mass of the dark photon is lighter than the wavelength you're looking at, then it has no effect.
Other questions? Yeah.
In the known nodes, you didn't discuss things like angular distributions and decays, or those sensitive to different sorts of things you talked about, or you think they're less sensitive, or any comments about that?
Well, that's a good question. So I talked, for example, about invariant mass in dileptons. So I was taking a one-dimensional kinematic slice, and indeed, angular information would be sort of an orthogonal slice, and a two-dimensional kinematic fit would potentially have much more power, and that is something we're still exploring. So we're sort of, as a first step, we found interesting sensitivity with one dimension mass, but then adding angles could add more. And in terms of decays, well, I mentioned Higgs decays would be one case, and getting from 10% to 1% would be sensitive to many types in new physics, too. So I think there could be unknown knowns in Higgs decays.
Did I hear correctly that for known left, upper left, known, yes, your current collider gives you confidence of 3 sigma?
Yeah, in 2038, but yeah.
And the new one, super pooper machine, will give you 5 sigma?
Yeah, 2055, say.
That seems very pessimistic. We spent all these billions and billions and billions to go from 3 sigma to 5 sigma.
Nobody before me even talked about trying to measure this thing. So it's a prediction of the standard model that's viewed to be very hard to measure. The LHC is for finding the Higgs and for finding other particles. So this wasn't. I'm finding new ways to use it that are hard, but that's something we can keep doing. And I'm trying to eat more salads.
Yeah, I don't think he's saying
You just eat less overall.
Yeah, nobody.
I am impressed.
Before our paper, nobody talked about doing this measurement at all. So it wasn't a goal. It wasn't part of the $10 billion justification.
I see. So the machine is not explicitly for that purpose.
No, not at all. So this was a new purpose we thought of, and there are many things. There's a super diverse space of things you can imagine doing. It's sort of so part of the game is thinking of new ways to use the data, and that was the spirit here.
I think if you're going to spend $10 billion, you want to make sure that you get everything you can out of it, right?
Okay.
Other questions? Again? Okay, Hog.
Well, I just wanted to give you an opportunity to say something about that, the point you just made, which is if these colliders produce such rich data and they have certain goals, but they have lots of other things that they're not looking at, does that suggest things about how these experiments should operate in terms of data release and public data and open code and open science?
Absolutely. So Kyle here is sort of one of the leaders of this, but we're trying to come up with ways to make the data public. Right now, the data are not public and can only be analyzed by the experiment. And then indeed, I did super simple things that I could do as a theorist of one-dimensional distribution and seeing new sensitivity. But really, you want to look at multiple higher dimensional space of the data and get more sensitivity, and people are developing machine learning techniques. Kyle's, again, one of the leaders there, but even with simple one-dimensional things, there are new things to say, but then I think the long-term goal as we get to 2038 is going to be to look at this in a high-dimensional way and try to look at the effects of multiple operators at once, and it can.
I was going to just make a point on the bottom right, which is in terms of the unknown unknowns, you don't really know what to do, but to the extent that like you just try to imagine as many things as you can. I mean, I think it's also at the LHC, there's a big change since we haven't seen stuff that people are trying to change the mindset to just sort of gear up for looking for more unexpected stuff. And actually, you know, there's a lot of experimental effort on that, but it's also kind of still very useful to have ideas. And actually, like some of the earliest work when you first came here with this like lepton jet idea were examples of things where it's very easy to explain to experimentalists, here's a signature in the data that we should be able to see. It was not motivated at all before. So I think it's also like you get some credit in the bottom right at the LHC program in terms of helping drive people to look for signatures that were not motivated by the traditional things and opening their minds just by giving examples of weird looking things that no one expected. So
Yeah, and those lepton jet searches are still happening, so that kind of seeded direction.
So, because there is an upper bound for the mass range in dark matter. So in terms of dark matter searching, would that be not so helpful for the colliders to go to higher energy? I mean,
We're not even at the energy in colliders where we can test the simplest versions of the WIMP, in fact. So like the simplest WIMP would be a Higgsino doublet of SU2, and that the LHC will not see if it's at 1 TeV where you would have the right abundance.
okay.
And even 100 TeV colliders turns out to be very hard. So we're nowhere near the Unitarity bound. Actually, in terms of robust collider limits, we're still actually in the core WIMP region. So it's very motivated to keep you going after dark matter candidates with colliders, in my opinion.
But not for MEV or KUV dark matter.
Lighter.
Yeah.
Well, that it depends now. If you have a mediator that you can make that decays to it, that becomes much more model dependent. Because if it's very light and weakly coupled, then the collider ends up not being the best way to look for it, except in cases where you have a mediator that decays.
All right, well, I'm sure people want to get to the refreshments, which are they
In a place.
they're in the usual place?
I don't know.
Eighth floor.
Eighth floor.
Usual.
Eight floor.
If they're not there, then go somewhere else. All right, thanks, Josh.